Hi from hi to Hamburg from Toulouse in France. My name is Arne, third year PhD here at Lagos. Happy to present some part of my work on eddy-internal tide interactions around New Caledonia, which is an official adopted crossover calibration and validation site of the SWOT satellite mission, which has been finally launched now in December. And certainly this work is in strong cooperation with my supervisors, Sophie Cravat and Lionel Godot here from Toulouse, and many others from colleagues from Grenoble and from Brest, as well as collaborations with Brian Arvik and also Kyla Druschka from the University of Michigan and Washington, respectively. So first things first, what makes New Caledonia such a great site to study these eddy-internal tide interactions? First of all, it's a region of complex circulation. We have all these westward propagating zonal jets and countercurrents, which are subject to barotropic and baroclinic instabilities. So giving, just rise to meso and sub-mesoscale active region with a lot of eddies and fronts. Second, it's a region of complex bathymetry with several ridges and seamounts of different spatial scales, so giving rise to major formation sites of internal tides. And third, the region where we expect eddies and internal tides to interact is located just beneath the satellite ground track of SWOT during its fast sampling phase, during which SWOT will be in a one-day repeat orbit, so collecting high frequency and high resolution sea surface height measurements. And it's also this region which will be subject to a dedicated field campaign in March and in April this spring, not only to collect valuable data from the three-dimensional water column, but also to evaluate the SWOT data. So for today, I would mainly like to introduce you to the tailored high-resolution regional modeling effort that we set up for this project. Then I give you a short description of the internal tide field around New Caledonia before addressing tidal incoherence and variability, and finishing with some insight into the impact of tidal forcing on the meso and sub-mesoscale, which is still ongoing work. So starting with the regional modeling effort around New Caledonia, more details are actually presented in the following paper listed below here, in case you are interested, which is ready for submission in Ocean Science. But yeah, in fact, together with Ocean Next in Grenoble, we set up this multi-year regional high-resolution simulation, which is called Caledo 6T. Which is located here in the Southwestern Tropical Pacific, which has a resolution of 1/60th degree and hourly output, which in turn is embedded in the host grid, which is called Tropical 12, which covers most of the tropical and the subtropical Pacific. Note that this is a forced model, so not coupled to the atmosphere. At the lateral boundaries of Tropical 12, we applied a barotropic tide forcing based on the Barotropic Tide Atlas FES 2014 and forced by the 5 major tidal constituents. Otherwise, we have 125 vertical levels, and setting this barotropic tide forcing at the lateral boundaries of the host grid allows us for a free wave propagation from the host grid into the regional domain. And moreover, we implemented a two-way nesting framework for our regional nest, so allowing for a two-way interaction between the host grid and the nesting grid. And I didn't mention it, but it's also NEMO code-based. And in addition, we set up a twin simulation with the exact same configuration than the one before, but without barotropic forcing, so with the goal to understand what impact tidal forcing has on or the modulation of energy pathways and in general on the meso and the sub-mesoscale, the background flow. Yeah, I will not go too much into detail on the model validation, but the model does perform well in terms of regional circulation, energy levels, especially in the internal wave gravity continuum, spatial patterns of eddy kinetic energy, and also the correct representation of the barotropic and the baroclinic tide, here expressed by sea surface height, showing good agreements with empirical estimates, here shown for the M2 or the semidiurnal tide, which is strongly dominating in our region. So comparing well with the FEST 2014 barotropic tide model, and also with the H-red product for the baroclinic part. So making us confident that our model is capable of studying eddy-internal tide interactions. Yeah, starting with a short description of the internal tide field characteristics around New Caledonia, which has not been studied and quantified before in such detail, even though it has been known as a hotspot of internal tide generation, as we know from satellite altimetry. So based on a harmonic analysis in a vertical mode decomposition here for each grid point, and based on a full model year, I show you here the M2 barotropic baroclinic conversion, revealing the major hotspots of internal tide generation in our regional simulation around New Caledonia, mostly associated with the main bathymetric features, of course, and yeah, in those regions, up to 70% of the barotropic tide might be lost and is converted to baroclinic energy or internal tides. But it's also in these regions where energy dissipation might be quite high, so meaning that up to 50% of the locally generated energy dissipates nearby, close to the generation sites. And yeah, as shown here exemplarily in the bar plot to the left, for the region of the major internal tide formation south of the main island. And this is a zoom into this region, which is, of course, important from an observational point of view because of the field campaign that I've just mentioned. We clearly see here that most of the internal tide generation to the left is happening at the Pines Ridge, from which the baroclinic energy propagates within a well-confined tidal beam towards the open ocean to the northeast and to the southwest. Strongly dominated by mode 1, actually, and with baroclinic energy fluxes of up to 30 kilowatt per meter. And yeah, we'll see constant dissipation rates along the continental shelf and elevated dissipation around the seamounts, which is then also important for internal tide-driven vertical mixing processes in a region such as New Caledonia, which is known as a hotspot of biodiversity. But in terms of tidal energy levels, this region is certainly comparable with the other major internal tide hotspots in the Pacific Ocean, such as the Luzon Strait near Taiwan or the Hawaiian Ridge. So this is, of course, concerns only the coherent part of the tide, so the phase-locked tide. Here we address the incoherent tide, also referred to as the non-phase-locked tide, which can form through the temporal variations of stratification, or as we have heard before from the other presentations, through the interaction with background circulation and the turbulent flow. So decomposing our total semidiurnal energy flux, we look at the coherent part of the signal and the incoherent part of the signal, where the incoherent part is expressed here as a ratio to the total semidiurnal energy flux. In the annual mean, we clearly see that a large part of the total flux is explained by the coherent tide, especially close to the generation site. But incoherence gains in importance with increasing distance to the generation sites. Exemplarily shown here for the southern tidal beam, where it eventually becomes the dominant signal at several hundreds of kilometers away from the generation sites. And also we see that the energy levels of incoherence are elevated in the southern domain. This is linked to mesoscale eddy activity, which is elevated south of New Caledonia. We will see this in a second. And yeah. So the interaction with the mesoscale eddy field is also here seen and illustrated by a 5-day snapshot of the incoherent energy flux, which is overlaid by the mesoscale circulation or eddy field. And also, as suggested just by Peter, we see that the tidal beam is clearly deflected and refracted in the far field. And this is associated with rim currents of the mesoscale eddies. And we have strong energy fluxes of the incoherent tide of up to 10 kilowatts per meter. And of course, tidal incoherence can also arise from the temporal variability of the conversion term at the generation sites. So showing you here the monthly conversion anomaly for April for the given model year, where the negative conversion anomaly averaged for the Pines Ridge here south of New Caledonia is clearly associated with variations in stratifications, which are expressed here in the inlet by pressure amplitude variations at the ocean bottom, and which in turn are induced by, again, mesoscale eddy variability, as shown by the elevated levels of eddy kinetic energy. So on top of this map, I also plotted a representative snapshot of the mesoscale eddy field, and this eddy that lies over the generation site persists for almost the entirety of the month there, and does not only influence the conversion, but also then, of course, the propagating energy, the baroclinic energy flux divergence. So finally, rather some preliminary results in the last part of my PhD, the impact of tidal forcing on meso and submesoscale. So addressing the question how tidal forcing impacts the transfer of energy in the ocean. And as a first approach, we looked at mesoscale eddy kinetic energy levels in both simulations. So the one without barotropic tide forcing to the upper left, and the one with tidal forcing to the upper right. From this, you can also see that eddy kinetic energy levels are increased south of New Caledonia. This is because of a regime shift from nonlinear to linear dynamics as we approach the northern half of the domain towards the equator. But on top of this, we see that eddy kinetic energy levels seem to be elevated in the tidal run in those regions where mesoscale activity is high, and also in the domain average. So this remains to be investigated in more detailed. But otherwise, what we have done is to differentiate between summer and winter, from which it appears that, in fact, tidal forcing has the biggest implications during summer months in our region, where energy levels are increased across all spatial scales. So here looking at the red solid line for the tidal simulation and the red dashed line for the non-tidal simulation for the summer months. Whereas in winter, there are no large differences seen, only at the large mesoscale, suggesting that the submesoscale turbulence dominates during this time of the year. And yeah, to go a bit further, we also computed spectral energy fluxes, as just introduced by Robin. And again, we don't see big differences for winter, except that the tidal forcing might shift the transition scale between the forward and the inverse energy cascade to larger scales in winter months. So looking here at the blue solid and the blue dashed line. However, in summer, also previously found, we have a huge forward cascade, which is introduced by the tidal forcing, which is otherwise almost non-existent. And on top of this, we also see indications of a slightly enhanced inverse energy cascade in summer only. But of course, these are preliminary results. Also, one of the reasons why I attend this seminar to learn a bit more on this. Also, we try to apply a coarse graining approach, which seems to be more robust and gives us a better idea about the spatial distribution of energy transfer. Yeah, to sum it up, introducing New Caledonia here as a region of strong eddy-internal tide interactions. To study these, we set up a unique high-resolution modeling effort with and without barotropic tide forcing, which gives us nice results so far. We do link the departure of tidal coherence to mesoscale eddy variability, both in the near and in the far field. Well, we see that we have indications that tidal forcing impacts and enhances both actually the forward and the invert energy cascade. But further work will be done on this in the upcoming months. But otherwise, that's all from my side, I believe. I'm happy to answer any questions in case you have some. Thank you.